This is the B-2 Spirit bomber, and it is, without a doubt, the best stealth bomber ever made. But while its ability to hit any target anywhere in the world makes the headlines, there's a secret army of maintenance that goes on before each mission. Get any one of the several thousand steps wrong, and this 2 billion aircraft becomes the world's most expensive lawn dart. It all starts here, inside the 509th Munitions Squadron's assembly facility. Airmen are preparing the weapons that will eventually sit inside the bomber's internal base. This building is climate-controlled because the guidance sections on these bombs can't tolerate dust or humidity. The temperature stays locked at 68 degrees, not for the technician's comfort, but for the ring laser gyros inside the guidance kits that will drift if the temperature swings more than just a few degrees. The first step is attaching the MAU-169 guidance section to the front of the weapon. This is where things get interesting. Inside this guidance kit sits a GPS antenna no bigger than a hockey puck. Below that, an inertial measurement unit with accelerometers that can detect movements smaller than the width of a human hair. The control module takes targeting data from the aircraft and generates commands for the fins. But here's the critical part: the umbilical connector. This is what allows the B-2 to talk to the bomb while it's still inside the aircraft. Without this connection working perfectly, you've got a very expensive paperweight. Technicians use torque wrenches to attach the guidance section. Too loose and vibration will cause it to fail. Too tight, and you crack the housing. Then they bolt on the tail kit, which holds the fins and actuators. These fins aren't just metal flaps. Each one is independently controlled by electric motors that can adjust position in increments of 1/10 of a degree. Before any JDAM leaves this building, technicians run the actuators through program movements to verify nothing binds. A fin that sticks for even half a second means the bomb misses by 100 feet. Next, they weigh the finished weapon, because the B-2's mission computer needs exact numbers for ballistic calculations. A 5-pound difference changes the timing. During all of this, one rule never changes: the JDAM is completely safe. This means the fuse is unpowered. The guidance kit is in test mode. The weapon cannot detonate under any circumstance. The thermal battery that powers the fuse won't even activate until it experiences the massive G-forces of being ejected from an aircraft. It is essentially a sophisticated lawn dart until the B-2 releases it. Once each JDM passes inspection, it's signed off in the weapon's database and loaded onto transport trailers. These aren't normal trailers. They maintain the same climate control as the building, because even a short trip across the tarmac in winter could affect the laser gyros. But loading doesn't happen yet, not until the bomber itself is proven ready for them. And getting a B-2 ready, that's where things get obsessive. Because unlike these weapons that need to be mechanically perfect, the B-2 has to be electromagnetically perfect. And that's a problem that requires maintainers to think in problems measured in millimeters. Out on the flight line, the 393rd Bomb Squadron's maintainers face their biggest enemy: physics. The B-2 stealth isn't magic. It's a careful manipulation of electromagnetic energy. That depends on the surface being absolutely perfect. Before anything else happens, before fuel, weapons, or anyone even thinks about an engine start, the low observable technicians get to work. The V-2 skin isn't painted like normal aircraft. It's covered in radar-absorbent material that's about as durable as a chalkboard. This coating contains tiny iron spheres that vibrate when hit by radar waves, converting that electromagnetic energy into heat. The problem is, this material is fragile. A bird strike, hail, even heavy rain can damage it. And damage means radar reflection. These technicians examine every inch of the aircraft surface. They're looking for chips, bubbles, scratches, or rough patches. The leading edges get special attention. This is where radar waves hit first. The engine inlets are critical too. Any imperfection here creates what's called a radar scatterer, essentially a beacon that broadcasts the aircraft's position. They check panel seams where different sections meet. Each seam is filled with conductive tape that has to be perfectly smooth. A gap the width of a credit card can increase the radar signature enough to make the aircraft visible on a bad guy's radar screen. When they find problems, and they always find problems, the repair process begins. They sand down the damaged area with precision tools. Too aggressive, and you create more radar reflection. Too gentle, and the repair won't stick. They mix special radar-absorbent compounds that have a working time measured in minutes. Apply it wrong, and you've just created a radar reflector instead of a radar absorber. Compound has to cure at exactly the right temperature, too. Too hot, and it bubbles. Too cold, and it doesn't bond. Once cured, they sand it flush with tools that remove material in thousandths of an inch. The final surface can't vary by more than the thickness of a few sheets of paper over any foot-long span. That's why B-2 maintenance takes so long. You're not just fixing an airplane, you're sculpting it. While the stealth techs work their dark art, other maintainers inspect the mechanical systems. The B-2's hydraulics operate at pressures that could cut through steel. 4 separate systems provide redundancy. Lose 1, you're fine. Lose 2, still flying. Lose 3, you can land, but you'll need new underwear. The flight control actuators get checked for any sluggishness. On an aircraft without a tail, every control surface is critical. Landing gear, brakes, tires, everything gets inspected. The environmental systems that keep the pilots from freezing at altitude. The electrical buses that power everything from radios to bomb release mechanisms. If any of these fail the check, weapons loading stops. The aircraft has to be perfect before a single bomb goes near it. Once the aircraft passes all checks, weapons loaders roll the jams into position under the aircraft. Each bomb sits on a hydraulic lift that will raise it into the weapons bay. Unlike every other bomber in the inventory, the B-2 cannot hang anything externally. Everything goes inside, or it doesn't go at all. The weapons bay doors are massive. Each one weighs about as much as an SUV. They open on hinges that have to be perfectly aligned, or they'll create radar reflections. Inside the bay is the rotary launcher. This is where the B-2 gets clever. Think of it as a revolver cylinder scaled up to hold bombs. 8 positions, each one capable of holding a 2,000-pound weapon. The entire assembly can rotate 360 degrees in under 3 seconds, which sounds smooth until you realize it's spinning 8 tons of high explosive, fast enough to make the whole aircraft wobble. Weapons attached to suspension hooks rated for forces that seem absurd. 14,000 pounds per hook for a 2,000-pound bomb. But that's because during combat maneuvers, G-forces multiply everything. A 2G turn makes that bomb weigh 4,000 pounds. Add turbulence, and suddenly those overbuilt hooks make sense. The mechanical interface has to align perfectly. Missed by the width of a penny, and the weapon won't receive power or data. Load crews lock the lugs that hold the weapon. They contain the cables that allow the JDAM to communicate with the aircraft store's management system. This is critical. Without this connection, the bomb never receives its targeting data. It would fall like any regular gravity bomb, missing potentially by miles. However, the coordinates aren't loaded into the bomb just yet on the ground. The bomb doesn't know where it's going. That information stays in the aircraft's mission computer until seconds before release. This isn't just security. It allows targets to be changed in flight, adapting to battlefield conditions in real time. Even fully loaded, the weapons remain inert. The fuses stay unpowered. The guidance systems are essentially asleep. The only functions that work are basic communication and diagnostic tests. The entire design philosophy is to keep the weapon as dumb as possible until the last possible second. It's safer that way. But once the plane is loaded, the ground crews need to ensure the pilots are safe too. At the 509th Operational Support Squadron's Aircrew Flight Equipment, or AF shop, specialists prepare the gear that keeps B-2 pilots alive at altitude. The B-2 flies high enough that a depressurization event would be fatal without immediate access to oxygen. The B-2's altitude ceiling is classified, but it's high enough that the pilots need pressure suits, not just oxygen masks. AF specialists connect masks to pressure rigs that simulate high-altitude breathing. The mask has to deliver oxygen even when the pilot is pulling Gs. When the simple act of breathing feels like someone sitting on your chest, they check the microphone. Communication has to work perfectly, even with oxygen flowing. In an emergency, there's no time to troubleshoot any communication problems. The helmet alone costs more than most people's houses, but it's not just protection. It contains heads-up displays, night vision compatibility, and flash protection that can block the blinding light of a nuclear detonation. The visor can go from clear to completely opaque in milliseconds, faster than the human eye can register pain from intense light. They inspect the survival vest with its emergency beacon, signal mirror, and water purification tablets. Everything designed for the possibility that a B-2 crew might have to eject over hostile territory. The anti-git receives special attention. Its inflatable bladders have to hold exact pressures. Too low, and the pilots black out during maneuvers. Too high, and it restricts breathing. These suits are custom-fitted to each pilot. What works for someone who's 6'2" won't work for someone who's 5'8". In the B-2, where missions can last 40 hours with air refueling, comfort isn't luxury, it's operational necessity. Once these checks have been completed, the ground crew then performs one of the most dangerous maintenance evolutions in the U.S. Air Force. Most refueling happens with engines off, but in a hot pit refueling, the engines keep running. The B-2's 4 engines stay at idle, each one generating enough heat to melt aluminum. This happens when the aircraft needs to turn around quickly. No time for the hours-long shutdown and restart cycle. Fuel crews approach wearing silver proximity suits that make them look like astronauts. These suits can handle short exposures to extreme heat. Just enough time to disconnect a fuel hose if something goes catastrophically wrong. They carry fire bottles capable of shooting suppressant foam to 30 feet. Everyone moves deliberately. The first step is grounding. The aircraft builds up static electricity in flight. Thousands of volts looking for a path to ground. One spark near fuel vapors, and the explosion would be visible from orbit. The grounding cable is as thick as a garden hose clamped to a specific point on the landing gear, where the metal is bare. They connect high-flow hoses to the single-point refueling port. Fuel flows at 600 gallons per minute. The entire process takes less than 30 minutes to load 167,000 pounds of JP-8. But it's not just about quantity. The fuel has to be distributed correctly across the B-2's tanks. Too much weight forward, and the aircraft becomes nose-heavy. Too much aft, and it becomes unstable. The flying wing design has no tail to provide stability, so weight distribution is everything. The fuel has to be the right temperature, too. Too cold, and it won't flow properly through the engines. Too hot, and it creates vapor bubbles that can flame out an engine. Crews monitor temperature, pressure, and flow rate constantly. The noise is overwhelming. Each engine sounds like a continuous explosion. Hand signals are the only communication that works. When refueling is finally complete, the B-2 is loaded, fueled, stealth certified, and finally ready for its crew. The pilots enter through a hatch behind the nose gear, climbing a ladder into the cockpit. They strap into ejection seats that cost more than a college education. These aren't just chairs. They're survival systems, capable of shooting the crew clear of the aircraft in less than a second, even if the B-2 is inverted or at 0 altitude. The crew connects oxygen lines, plugs into the intercom, and begins the startup sequence. The B-2's cockpit is a glass panel of displays and keyboards. No steam gauges here. Everything is digital. The mission computer alone has more processing power than the entire Apollo program. But all that technology means nothing if the initialization sequence isn't perfect. The inertial navigation units begin their alignment for 8 minutes. The aircraft cannot move, not even an inch. The ring laser gyros are measuring the Earth's rotation to establish their reference. Interrupt this process, and they have to start over. GPS loads next, but not just civilian GPS. Military GPS that's encrypted and accurate to within feet instead of yards. During taxi, the pilots run control surface checks. The B-2 has no rudder, no vertical surfaces at all. Yaw control comes from split drag rudders at the wingtips, surfaces that open like air brakes on one side to induce a turn. If these don't work, the aircraft can't maintain coordinated flight. The elevons move through their full range, up, down, differential for roll control. Each movement verified by multiple sensors, because on a flying wing, one failed control surface means loss of aircraft. Even the taxi itself requires planning. The nose wheel is 110 feet ahead of the main gear. The pilot has to think that far ahead for every turn. Too sharp, and the main gear goes off the taxiway. It's like driving a semi-truck, but in reverse, except the truck weighs 336,500 pounds and costs $2 billion. They brief the takeoff, rotation speed, abort criteria, emergency procedures if an engine fails. The B-2 needs most of the runway at max weight. There's no margin for error. Rotation speed comes fast. Once you pass that point, you're going flying whether you want to or not. The throttles advance. 4 engines spool up from idle to military power. The acceleration pushes everyone back as 69,200 pounds of thrust fights 336,500 pounds of aircraft. The nose wheel lifts first. Then, finally, reluctantly, the massive wing generates enough lift to break free from the runway. At altitude, the B-2 cruises in air so thin that the engines produce a fraction of their sea-level power. The aircraft is on autopilot, but the flight control computers make constant adjustments, 1,000 corrections per second to keep this tailless aircraft stable. Without these computers, the B-2 would depart controlled flight in seconds. As they approach the target area, the crew runs through the weapons checklist. They select which JD dam to drop first. The rotary launcher inside the bay begins to move, rotating the chosen weapon to the release position. The weapons bay doors remain closed. Opening them too early would light up every radar screen for miles. When the moment comes, the doors open for exactly as long as necessary. No longer. The sudden change in airflow causes the aircraft to buck. The flight computers immediately compensate. Now, finally, the JDM wakes up. Through the umbilical connection, the mission computer floods the weapon with data. GPS coordinates to 10 decimal places, wind speed and direction at multiple altitudes, barometric pressure, time to impact, the planned angle of attack. The JDAM's internal computer processes all of this in milliseconds. It runs diagnostic tests on every subsystem. Fins operational. GPS receiver acquiring satellites. Inertial navigation aligned. Battery ready to activate. Everything happens in the space between heartbeats. The release sequence happens in fractions of a second. The suspension hooks open. Pneumatic ejectors fire, pushing the bomb clear of the aircraft. The JDM falls away at 4 feet per second. Fast enough to clear the bay, slow enough to remain stable. The instant the umbilical breaks, everything changes. The thermal battery ignites, reaching operating temperature almost instantly. The fuse begins its arming sequence, sensing the required G-forces, waiting the required time delay. The tail fins unlock and deploy. The GPS receiver locks onto satellites. 4, then 6, then 8. The more satellites, the better the accuracy. Inside the JDAM, the mission computer is running calculations at a rate that would have required a room-sized computer in the 1990s. It knows where it is. It knows where it needs to be. It calculates the optimal flight path. Not a straight line, but a complex curve that accounts for wind, air density, and the Earth's rotation. The fins make their first adjustment 2 seconds after release, a slight bank to the left, compensating for a crosswind the B-2 sensors detected. The JDAM doesn't fly, it falls with precision. Each fin movement trades altitude for lateral movement, gradually walking the impact point toward the target. If GPS gets jammed, the inertial system takes over. It's not as accurate, but it's good enough. 30 meters instead of 10. The bomb continues to make corrections, smaller and more frequent as it descends. In the last 10 seconds, the bins might adjust hundreds of times. Movements so small, they look like vibration. The radar altimeter activates in the final moments, giving precise height above ground. The mission computer calculates exact time to impact. The last correction appears fraction of a second before impact. A tiny adjustment that moves the impact point by just a few feet. And then it hits. Bye for now.